Hi guys, this is Mr. Ho here. Right now I should be in Shanghai together with the Form 4 student in the exchange program. But like I said before, we will have a video class, so do not ever think of having a self-study period. It never happened in my class, okay? So let's get started. Please take out the chemistry of carbon compound part 2, and today we will finish a huge part of the last topic, right? So let's go to page 86, and let's get started. So last time we have talked about aspirin, and you know aspirin is a painkiller, and we have learned some of its chemistry involved. And as a quick revision, so aspirin, another name of it is acetylsalicylic acid. So you have to know that the main effect of it is it can relieve mild pain, so as a painkiller, but at the same time, it can also help to reduce inflammation and fever. So in Chinese, we always say these 4 words to represent its function. And it also have the function of thinning the blood. That means it can prevent blood clotting from happening and therefore reducing the incidence of heart attack. But there are some side effects about aspirin. In fact, we no longer use it nowadays. We use other painkillers such as paracetamol, also known as Panadol, because aspirin is known to have a side effect of irritating our stomach wall, causing peptic ulcers. And also some of the people are allergic to aspirin and some other problems associated with aspirin. So we don't really use this one anymore. Now, also, you have to study the structure of aspirin. Actually, this is the aspirin tablet that we will use, but its precursor would be salicylic acid, and you notice that it is actually a carboxylic acid with a hydroxyl group here. So if I ask you what functional group it has, so you should tell me that it has a carboxylic group, it has a benzene, as well as an hydroxyl group. And actually, with benzene and hydroxyl group, we will call it a phenol group. So you can jot down here. So benzene together with the hydroxyl group, actually the whole thing can be described as a phenol group. Okay? And phenol is a little bit special because despite it looks like a hydroxyl group, but it is actually acidic. Alright, it is actually acidic. So you realize that for salicylic acid, because it has the carboxyl group and the phenol group, which are both acidic, so actually salicylic acid by itself is quite acidic. So that's why we have to undergo this esterification, try to convert this phenol group into an ester, so that we can reduce the acidity, so that it will less likely to cause the peptic ulcers. Now this one you have learned before, it is esterification, so we are talking about the alcohol and the carboxylic acid undergoing a esterification to form an ester. So that you know aspirin is actually an ester. Don't forget we have a water being produced, reversible reaction, consulfuric acid as the catalyst, and we have to heat it under reflux. Alright? So these are the functional group present in aspirin. Make sure you notice that. And you know, aspirin, looking at the structure, it is slightly soluble in water because of the hydroxyl group and the slightly polar ester group. But it is not very soluble in water when compared to, let's say, ethanol and ethanol acid. So about its solubility, we will later on talk about it. Okay, so right now, after the revision, I would like you to spend some time working on this question. I would like you to spend around 5 minutes, try to go through all the questions, and after 5 minutes, I will check the answers with you guys. So may I ask, maybe subject representative, please help me to pause the video for 5 minutes and then resume, all right? All right, I suppose 5 minutes has been passed, and I suppose you have already at least go through those questions. So let's quickly discuss about it. So this is aspirin. It is made from salicylic acid. It has its structure shown here, but this one is not aspirin. This is salicylic acid. So one medical use, of course, is to relieve mild pain. Now the word mild is not important, or you can say reduce inflammation or fever. Now salicylic acid can be converted to aspirin by reacting with ethanoic acid. So first of all, state the type of reaction. Now this one I expect you to put down condensation because it is asking about the type. But if you put down esterification, I believe it is also acceptable. But if you ask me, this is better because it is the type of reaction. Now, the second part, write down a chemical reaction for equation for those reactions. So make sure you put down the structural formula for any reaction or equation concerning about organic compound. So with the ethanoic acid, CH3COOH, make sure you use a reversible sign so that you won't get deducted by 1 mark because of the wrong use of the arrows. And make sure you have a water that is formed. All right. So just like that. Now C1, it says that aspirin, already the product here, can be converted into an ionic salt by reacting with dilute sodium hydroxide, and you are asked to write a chemical reaction again. Now you notice that this one, sodium hydroxide, thinking about the reaction of ester, probably you will think about hydrolysis, right? But you think about it, is there any heating? There's no heating involved in these reaction conditions. So therefore, hydrolysis may not be the major reaction. So instead of doing a hydrolysis, actually, do not forget that we still have a carboxyl group here. And the carboxyl group is acidic. When you treat it with sodium hydroxide, it's going to be an acid-base reaction or neutralization reaction. So this is what I expect you to write. It should be a neutralization reaction with the carboxylic acid. A little bit ugly, but it is another way of representing it. So react with sodium hydroxide. Now this one is acid-base reaction, so you use a single arrow. Don't spam the use of reversible arrows. Okay, and remember, again, this is a neutralization reaction. Water should be produced as one of the products. Okay, and C2, it says that some of the aspirin are made into ionic salts. So basically, some of the aspirin, they are made into this form rather than this form, all right? Made in this form rather than this form, and which has a better painkilling effect in our human body. So based on the structures of aspirin and ionic salt, explain why the ionic salt has a better medicinal effect. Now this question could be challenging, but the hints were given, which are the structures we have to compare. Now comparing these two, one is a molecular form, one is a ionic salt. So based on the structure, what we can think about would be melting point and water solubility. Now I believe the melting point does not really related to the medicinal effect, while our body is only like 37 degrees Celsius. Well, if you have a fever, that could be 40, but not that hot to melt it, isn't it? So I believe it has to do with the water solubility. So if you compare these two, which one is more soluble in water? It has to be the ionic form, the ionic form, especially with sodium ion being the positive ion, because you remember all the salts made of sodium ions are soluble in water. So basically, the ionic salt is more soluble in water than this one. So what would be the advantage of it? So it's more related to biology. If something that is more soluble in water may as well be more soluble in the water of blood, right? And you know the drugs must be carried to the site of effect through bloodstream, right? So if this is more soluble in water, you expect to have a higher concentration of aspirin dissolved in the water of blood. Or you would say the aspirin can reach the site of effect faster because of higher water solubility. So this is the two things I would like you to mention. So first of all, regarding the structure, we say that um, the ionic salt bear, now it's quite obvious because it has to compel the structure, while aspirin does not. Therefore, the ionic salt is more soluble in water. So I am anticipating more soluble in water. Okay. So how does it lead to a better medicinal effect? Then you will tell me that there will be a in the simplest way, the ionic salt dissolves in water of blood better, thus reaching to the site of effect faster. Okay, right? So I believe you have to connect it to the blood because this is how it is being transported around the body and also reaching the site of effect faster. Or you can say a larger concentration of aspirin. Okay, so this is what I expect you to write down. Okay. Now the last one is talking about both salicylic acid and aspirin. They are both useful in pain killing, but salicylic acid is more likely to cause stomach ulcer. So we just talked about it previously. Why salicylic acid is more likely to cause stomach ulcer. So the very simple thing you have to tell me is salicylic acid is more acidic. Okay, or you can say dissolves in water to cause a lower pH, or you can simply say more corrosive. Okay, so you talk about some of the property related to acidity. That is what I expected to see. All right, so that would be the aspirin. Okay. Now, next part is about soap and detergents. Soap and detergents. So first of all, we often compare the structure, the function, the properties of soap and soapless detergent. Well, detergent or soapless detergent, so if you can look at some examples, they have some similarity and difference. So according to the color, as you can see, they both have a very long hydrocarbon chain, And they also have the blue part, which bears a charge, which bears a negative charge. So in this case, this is carboxylate group, carboxylate ion. This one is some kind of sulfate that looks like sulfate. Okay, and well, we have several types, but they are similar. Okay, they are similar. They have some kind of sulfate anion head. Okay, and because they are the salt, so not only they have the negative part, they also have the positive part. Usually we choose sodium ion or potassium ion because noticing such a huge anion, if you choose some ions other than sodium and potassium, the whole thing is not likely to be soluble in water. So usually sodium ion will be accompanied with the huge anion to make them soluble in water. Okay, so you don't really have to memorize the name, but you need to focus on the structural features because I can give you the structure of either one of these and then ask you which one is which. At least you are able to tell. So simply put, with the carboxylate ion, it's going to be soap. With the sulfur-containing anion group, it's going to be detergent. All right? Now, let's talk about their origin. So what is the raw material of making them? For soap, they are made from fat and oil, so more of natural raw material. And there is a process called saponification. Saponification. So saponification is actually a process to make soap, to simply put. So now here, this is an example. This is, if you study biology, this is a triglyceride. And if you didn't study biology, this is simply an animal fat. And we can also say this is a triester because you can see there are 3 ester groups. 1, 2, 3. Right? So what we are trying to do is to undergo a hydrolysis, or to be more specific, alkaline hydrolysis. Alkaline hydrolysis. So we will add sodium hydroxide, and actually we undergo heating as well. So what it does is, recall your memory, we kind of split at the ester bond. And since we have 3 ester bonds, so it cuts here, it cuts here, it also cuts in here. Okay? So there should be 3 cuts on the animal fat. So after you cut it down, remember whenever you cut an ester bond, you have to slot in the H2O back. So if you remember, for the carboxylic acid part, the H2O will have its OH plug it back to the carboxylic acid, and with the remaining H, plug it back to the alcohol. All right? So that's why if you look at the whole animal fat, you plug in the H on the alcohol part, so H in here, H in here, H in here, resulting in a trialcohol or triol. Okay? And this one, if you study biology, you know this is glycerol. Glycerol. Okay? Glycerol has a sweet taste. So glycerol. And on the other side, where we plug in the OH back to the carboxylic acid, so we should have 3 carboxylic acids that are formed, or we can call it fatty acids. Fatty acids. But you notice, hey, the product is a little bit different than what we expected, right? It should be carboxylic acid. Well, why is it like an ion? Well, this is because this is alkaline hydrolysis. We have excess amount of sodium hydroxide. So when you once form the carboxylic acid, it will undergo acid-base reaction with the sodium hydroxide, forming a carboxylic ion. Okay, so you notice that we have basically an ion of fatty acid, and in fact, this ion of fatty acid is known as soap. Okay, it's known as soap. So actually, this is the soap. If you compare this back to this one, they are actually the same. All right. So this is how we can make soap from animal fat and oil. Usually, well, supposedly it is made from fat because it's supposed to be saturated, but we also convert plant oil into saturated by hydrogenation, and then followed by the hydrolysis, because simply plant oil are cheaper. All right, but basically these are the soaps. Okay. Now, what about soapless detergent? Now, the process of making soapless detergent is not required. All you have to know is they are coming from petroleum. So they are products from petroleum. Okay, you know the heavy fraction of petroleum, where it has more carbons, so they are chosen to be made petroleum to make a detergent. Okay. Now, another part that we have to learn about is action in hard water. Now, what do you mean by hard water? So, hard water, okay, you know, water is not hard. How come there is something called hard water? Now, it's not talking about the physical property, whether it's resistant to deformation or resistant to scratches. We are talking about the presence of minerals in the water, especially Mg2 plus and Ca2 plus. So the hardness of water is basically a measure of the concentration of Mg2 plus and Ca2 plus in the water. So to simply put, actually our tap water To simply put, actually our tap water is an example of hard water. If you recall your memory in Form 1 Science, in water treatment plant, we actually add some kind of calcium-containing compound or some kind of ionic salt inside, for example, alum. So it actually results in some of the ions in the water. And also we may add some lime, okay, to neutralize acidity to adjust the pH of the tap water, and that's why we have these ions inside. And of course from the natural source. Anyway, so what we're trying to say is actually soap and detergent, they have different action in hard water. So if you're talking about soap, so soap, it doesn't work in hard water. So this is one of the disadvantages of soap because basically the soap molecule, the soap ion will react with calcium 2 plus or Mg2 plus to form a precipitate. So, for example, calcium stearate. So this one is insoluble in water, and therefore you think about it, when you are using a soap in hard water, you will be forming this white precipitate as you use it. So it's going to be inconvenient and dirty, not desirable. We call this scum, okay? We call this scum. This thing is called scum, all right? So this is the idea. But what about detergent? If you have washed dishes at home before, do you expect to see some white solid form as you wash your dishes? Obviously not. So for detergent, it doesn't form scum in hard water. So therefore, we should say soap, it works in soft water only. But for detergent, it works in both soft water and hard water. Okay? Now, lastly, it's about the pH. For soap, it is always alkaline, simply because the way it is being produced is by alkaline hydrolysis. Well, if this is acidic, then you will have the ethanoic acid form, which is not desirable because later on we will talk about it. It doesn't have the cleaning effect. Plus, it smells quite bad because with free fatty acid usually smells very bad, like spoiled fat or oil. So it is undesirable. But the soapless detergent can be modified into acidic form, neutral form, or alkaline form. Most of them are in alkaline form, but we also get acidic form. Okay. Now, if we have an acidic form, just a little bit supplementary. If we have an acidic form, it will be very similar to the detergent like here. It still have a long tail, non-polar, but it will have a different kind of head. But this time the head is not negative, it's positive. So a very common example would be having an ammonium head. Okay, so it will bearing a positive charge. But at the same time, it will also have a negative anion outside to balance the charge. Okay, so this is another type of detergents which are actually acidic and is positively charged at the head. Okay. Now, so that will be the comparison. All right. The structural features, how are they being made? What are their origins? pHs. Okay. Now let's talk more about specifically a structure of a detergent molecule. Here we focus on the detergent molecule, but it has similar structural properties for soap as well. So for the long tail, we have a name. We call it hydrophobic hydrocarbon tail, hydrophobic. So this one, we call it in Chinese. So hydro means water. Phobic comes from the word phobia, like social phobia. That means you're afraid of it. Okay? So this is how the word comes from. And then, so water fearing, as you can tell from here. So this part, it's afraid of water because it's non-polar, but it is soluble in oil and non-polar solvent. On the other hand, the head we call it hydrophilic. So hydrophilic, hydro means water again, and philic means philia, means love, like. Okay? So basically the opposite of hydrophobic. With the anion, it is soluble in water, so it is a hydrophilic ion head. Okay? Now, so you notice that for a detergent molecule or even a soap molecule, it has two distinctively different parts. One is a hydrophobic hydrocarbon tail, another one is a hydrophilic ionic head. Okay? And these two are important for its function. Okay? And when it comes to the description, sometimes we will describe it as a tadpole-shaped because of the long hydrocarbon tail with a kind of like a spherical ionic head. Okay? And this structural property is important because it kind of explains the wetting property and the emulsifying property of detergent. Okay? For this, I will explain it later in part 2. Now, this is going to be part 1. So I will stop here and we'll resume in part 2. Okay?